Hello, this is Eric Hernandez. If you've taken a course in structural analysis, I'm sure you've seen this equation. Derivative of moment with respect to x equals shear, right? This is the moment equation, this is the shear equation, and if you take the derivative of the moment, you get the shear. That is based on doing the equilibrium of a differential element, right? Subject to shear on one side, on the other side, bending moment, and then uniform or any kind of distributed load which varies across the length, right? So this is M on one side, this is V on one side, this is V plus dV, this is M plus dM. And if you do the equilibrium equation of that and you do sum of moments, sum of forces, you arrive at this equation right here. And that's all fine. Unfortunately, there is a missing term that is often neglected in most books. And that's what I want to talk to you about today. What happens to this equation if, in addition to this distributed loads, you also include distributed bending moments, lowercase m here? Well, what happens is that then this equation becomes a little bit different. So let's see what happens. If we do sum of moments about this end right here, this is end I, this is end J. We do sum of moments about J, we find what? Well, we find M, we find V times dx, we find Q times dx over 2, right? That's the force times distance. V plus dV creates no moment because it's going right to that point. And then here we have minus M minus dm. And then we have an extra term that comes from the distributed bending moments M. And that term is going to be plus M times dx. All of that equals to 0. That m cancels with that m. This term here vanishes because it's of second order differential. And then you end up with this relationship here. dm equals v dx plus m dx. If you divide by dx on both sides, then you end up with this. dm dx equals v plus m as a function of x. So this is the more complete equation that includes the effect of distributed bending moments. So the derivative of the moment is not the shear unless the beam does not have any distributed moments. If it has distributed moments, you have to include mx. And for example, you could end up with cases where you have a beam with a shear diagram that is not 0 and a moment diagram which ends up being 0. For example, look at this case right here, simply supported beam, and I've discussed this before in a previous video, and this beam is only subject to uniform distributed moments M, and the length of the beam is L. If you go to a previous video that I uploaded, I'm going to share the link, you'll find that that beam has uniform shear, but it has 0 bending moment across its full length. So remember, derivative of moment is shear only if the beam does not have uniform or any other kind of distributed moments along its length. See you on the next post.